Richard James will present Decimal Tutorial 3, Part A. First, we are required to write the square root of the given number exactly. We imagine then that the answer should be a finite decimal, something that can be written exactly. Otherwise, its exact value cannot be written. Right, so if you have an infinite decimal, there is no way that we can write its exact value, because the decimal continues forever. We can write an approximate value, but not an exact value. So we imagine, because we are required to write the exact value of that number, we imagine that the answer should be a finite decimal. Otherwise, its exact value cannot be written. However, that may well be vain imagination, as we have experienced circumstances in which exact values have been solicited for irrational numbers. So although we are hoping, well, you know that we have done it already, but I'm just saying for the purpose of clarification that you will find circumstances in which the exact value of something is solicited and there is no way it can be supplied, especially in decimal form. Therefore, although we are using the cue that we need to write the answer for this one exactly, we are using that fact to come to the conclusion that we should be able to write it as a finite decimal. That is what we are doing. It is not necessarily the case that we will always be able to do this every time a problem says that we should write the answer exactly. As a matter of fact, I used a calculator in working out that square root that we have there. However, we may do it without the use of the calculator. Let us therefore go to the next slide where we will attempt to do it. Find the square root of this number with so many digits, and we will attempt that without the use of a calculator. And we are saying it is impossible. Well, we will see when we get to the next slide if that is impossible. We will use repeated division as we did in primary school in situations that we were required to find the LCM and HCF. We are familiar with that from primary school, and we will execute that on the next slide. Repeated division. And how are we familiar? When we were required to find the LCM and HCF, we use that repeated division by prime factors. We need to find all of the prime factors of the number. We will begin with 2. Any even number has 2 as a factor, and even numbers are those that end with 0, 2, 4, 6, or 8. So any number ending with those digits will be a multiple of 2, or an even number, and it will have 2 as a factor. We will divide until the number is exhausted. Begin with the number as if it has no decimal place. So let's go. We will begin with the number as if it has no decimal place. It ends with a 4, so we are sure that it is even, and we may divide by 2. And it is easy to divide this by 2. All we need to do is just use our eyes and separate this into some useful even numbers. So we say 10 is the first one. 2 into 10 is 5. 2 into 16 is 8. But do not forget this 1 that 2 cannot divide into. So we say 2 into 10, 5, 2 into 16, 0, 8, 2 into 0, 0, and 2 into 64, 32. So we should have 5, 0, 8, 0, 32. 5, 0, 8, 0, 32. Very nice. And that is our result. Then what do we say? 5 into 50. That is what? 25, 4, 0, 1, 6. 2 into 50, 25. 2 into 8 is 4. 2 into 0 is 0. 2 into 32 is 16. So, 25, 4, 0, 1, 6. No problem. Have some fun. Dividing by 2. Okay then, what do we say here? 2 into 25, we know that 12 and a half carry 1. But do not do that. Say 2 into 2 is 1. And then 2 into 54 is 27. Then 2 into 0 is 0. And 2 into 16 is 8. But do not forget that we need to include another 0 for this one. So we have what? 1, 27, 0, 0, 8. 1, 27, 0, 0, 8. And then what do we do next? 2 into that. 2 into this will give what? 2 into 12, 6. 2 into 70, 35. So 6, 35, 0, 4. Lovely. That's a lot of fun. Now we have 2 odd numbers following each other. How do we sort that out? Let's see. Alright. Well, it is good that those 2 odd numbers are followed by this 0. So we can say 2 into 35, 17 and a half. So we'll have 2 into 6, 3. Then 1, 7, 5. And 2 into 4 is 2. So 3, 1, 7, 5, 2. 3, 1, 7, 5, 2. So we are having a lot of fun with that. But what is horrible now is that we have 3 odd numbers following. But it is not difficult because we can just carry 1 all the time. So 3 into 31. So 2 into 31. 2 into 31, what's that? 2 into 30 is 15, carry 1. 17, 8, carry 1. 15, 7, carry 1. And then into 12 is 6. So let us say 1, 5, 8, 7, 6. Let's see, 1, 5, 8, 7, 6. Nice. And we say 2 again into 1, 5, 8, 7, 6. And what will that give? We have a 1 to carry. So we say 2 into 15 is 7, carry 1. So it will be have what? 7, 9, 3, 2. 7, 9, 3, 2. Let's see if that's right. 7, 9, 3, 8. So it was a little off there. Okay. So what do we do next? Continue dividing by 2. And we have 3, 9, 6, 9. Number does not end with an even number. 2 cannot go directly into this without leaving a remainder. But we are sure that 3 can go into it because 3 can go into this, 3 into this, 3 into this, and 3 into that. So since 3 can go into every digit, we know that that number is a multiple of 3. The number is not even anymore. we may discontinue the use of 2. All of the digits in the number are multiples of 3. We are sure that the number is a multiple of 3 because all of the digits are multiple of 3. We will continue by making use of 3. If the number is an actual square, a perfect square, then each factor must be used an even number of times. We are therefore sure that if this number represents a square, 3 may be used more than once. Therefore, if the number is a perfect square, for each factor that we have to have an even number of those factors. So 3 into this. 3 into this is 1, 3, 2, 3. Right. So as long as this is a perfect square, we may use 3 again, because in a perfect square we cannot have an odd number of any factor. So use 3 again. So what is that? 3 into 13, 4 times carry 1. 3 into 12, 4. 3 into 3, 1. 441. That's nice. And we know 441. We are not strangers to figures. We are not midgets to digits. Therefore, we are sure that the square root of 441 is 21. Any mathematician that is worth his salt should be able to identify 441 as the square of 21. But we will continue with the use of 3. 441 divided by 3 is equal to 147. Why did we continue with the use of 3? We are sure that if you add these digits, 4 plus 4 is 8 plus 1 is 9. Because 3 can go into 9, 3 can go into 441. And we are saying 147 times. Also, we know that we have to use another 3, because in a perfect square we cannot have an odd number of any factor. We have used 3 times already, and we may not have an odd number of any factor in a perfect square. 3 is an odd number. There is at least another factor of 3 in there. So because we have 1, 2, 3 odd number in a perfect square, we cannot have an odd number of any factor. Then we know that we need to have another 3 as long as it is a perfect square. And what do we know? 3 into 14, 4 times, and we bring 2. 3 into 27 is 9. And we are done, but we'll just continue an easy route all the way downhill, because 49 is the square of 7. Let us continue with a factor of 7. 7 into 49 is 7. Then we have a 7 alone. 7 into 7 is 1. And we are done. What we really wanted was the set of prime factors. Now that we have them, we will go to the next slide where we will pay attention to them alone and nothing else. Go to the next slide, pay attention to only the prime factors. There we have them. We are attempting to find the square root of 101.6064, but we are working with the number as if there is no decimal place or decimal point or decimal fraction, and then we will make the necessary adjustment in the end. In order to find the square root of the original number, we need to take half of the entire set. Half of the set. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We do not do this 1, 2, 3, 4, 5, 6, 7 chop off these and say that's half because 7 is up there and 7 down here. No, we cannot do that. When we say we need half of the number of factors, it means that we have to consider the 2's. Right there we have 8 2's. 8 divided by 2 is equal to 4. The square root will therefore have 4 factors of 2. So we take the 2's, 8 of them. The square root will have half of the number of factors, 4. There we have 4 2's multiplied together. Then we move merrily to the 3's. How many of them? There are also 4 factors of 3. 4 of them. Take half, so we take 2. The square root will therefore have 2 factors of 3. How many factors of 7? 2. Finally, we have 2 factors of 7. 2 divided by 2 is equal to 1. The square root will therefore have 1 factor of 7. When we multiply those, the result is 1008. As long as the square root of a number is rational, then the square root will have half of the number of decimal places as the original number. The original number, you can remember what the original number was? 101.6064. That is the original number with 4 places of decimal. The square root will have half of the number of decimal places. It will have 2 decimal places. So this is our number, and we need 2 places of decimal. So the number has 4 decimal places. The square root will therefore have half of that number. Half of 4 is 2. The number will have 2 places of decimal. There, 10.08. A rational number is a number that may be written as a fraction in which both numerator and denominator are integers. Square roots that have finite decimals are rational, but the converse, namely a rational square root, may be represented by a finite decimal. A finite decimal is not necessarily true. For example, there we have this, the square root of 16 over 9. It is written as 4 over 3. This is rational, but the decimal is not finite. The answer is expressed as a fraction whose numerator and denominator are integers. That's the answer. Numerator is an integer, denominator is an integer. What we are saying is that it is rational. That means that the original number has a rational square root. However, we know that 4 divided by 3 is equal to 1.33, going all the way with the 3 recurring. There is therefore no finite decimal representation of the answer, but it is rational. So there is no finite decimal representation of this number, but it is rational. It is the rational square root of 16 over 9. So the rational square root of 16 over 9 does not have a finite decimal. However, if the square root of a number has a finite decimal, then we are sure that it is rational. As it is said here, a rational number is one that may be written as a fraction in which both numerator and denominator are integers. square roots that have finite decimals are rational. So square roots that have finite decimals are rational. But the converse, rational square roots may be represented by a finite decimal, is not necessarily true. Reiterating, square roots with finite decimals are irrational and will have half of the number of decimal places that the original number has. Also, to find the square root of a number, divide the set of prime factors in identical halves. The product of those prime factors will be the square root of the number. Therefore, anywhere you see the square root of a number and it is represented in this way as a finite decimal, then we know that the number is rational. But not every rational square root may be represented as finite decimal, as we see that this one is not a finite decimal, yet still it is the square root of 16/9, and it is also rational. Write the answer correct to one decimal place. Locate the first decimal place one digit to the right of the decimal point. That's it. One decimal place to the right. So we are writing correctly to one place of decimal, and we are locating that first place of decimal as that first digit to the right of the decimal point. Then we check the digit that is next in order of significance, which is the one further to the right. The digit is 8, which is greater than or equal to 5, surely greater than 5. Therefore, we add 1 to 0, which is the digit in question. 0 plus 1 is 1. The other digits are not affected and return as they are. When rounding numbers, if the digit next in significance to the digit in question, which one is the digit in question? This one. Why? Because we are writing correctly to one decimal place, and this digit is in the first decimal place position, so it is the digit in question. So if this one is 5 or more, we add 1 to the digit in question, which is this one. In this particular case, the digit in question is the one in the first decimal place, and its value is 0. We may write the answer correct to two significant figures. Locate the second digit in order of significance by counting from the left, which is where we will find the most significant digit. Second digit in order of significance. What do we do next? We check the digit that is next in order of significance, the one to the right. And what? The digit is 0, which is less than 5. So we do not add 1 to this 0. And it returns like that. The other digits, well, in this particular case, it is a single digit, and we just return that single digit as it is. When rounding numbers, if the digit next in significance to the digit in question is less than 5, then 1 is not added to the digit in question, which is this one. In this particular case, the digit in question is the second significant digit, and its value is 0, this one. Finish up this section by writing the answer in standard form. Write that in standard form. The number needs to have one non-zero digit to the left of the decimal point. Count the number of places by which the number has to be increased or decreased in order that we may have one non-zero digit to the left of the decimal point. So we will have the understanding that only one non-zero digit needs to be to the left of the decimal point. And additionally what? Additionally, we need to count the number of decimal places that will allow us to be able to do that. The number is decreased by 1 place of decimal. The number is therefore divided by 10, which is the same as 10 to the power of 1. Reduced by 1 place of decimal is the same as dividing by 10, or dividing by 10 to the power of 1. Surely we have only one non-zero digit to the left of this decimal point. Also, 1 point something is smaller than 10 point something. Therefore, we are sure that we reduced by 1 place of decimal in getting here. Therefore, we need to recover lost ground by multiplying by 10 to the power of 1. We need to recover the original value of the number by multiplying by 10, or 10 to the power of 1. A number that initially had non-zero digits to the left of the decimal point is called a large number and will be accompanied by a positive power of 10 in the end. So here we have at least a single non-zero digit to the left of this decimal point. That number is therefore classified as a large number and is accompanied by a positive power of 10 in the end. Powers of 10 as usual. The first step that I have taken in solving this problem is to include a hidden step in which 10 to the power of 4 is written as 10 times 10 to the power of 3. 10 is then used to increase 4.8 by 1 place of decimal. Good if we can imagine or see this relationship between 4.8 and 24. How closely 4.8 is related to 48. And as a consequence, just 2 times 24 is 48. So if we can make that adjustment, then the rest of the problem is simplified. So in order to achieve that, what do? We take this 10 to the power of 4 and we write that as 10 to the power of 3 times 10. Take this 10 and increase this by 1 place of decimal, in which event we will retain the 10 to the power of 3, and this will be a total of 48. So the division process is simple. 48 divided by 12 is equal to 2, And when we are dividing numbers that have the same base, we subtract the indices. 3, because we are dividing, subtract the index of the divisor from the index of the dividend, and what do we get? 3 minus 7 is negative 4. So we have in this particular step just this conversion. 4.8 times 10 is 48, and then we have to retain this power of 10 right here, 10 to the power of 3 there, and 48 divided by 24 is 2, and when we divide, we subtract the index of the divisor from the index of the dividend, and we have 2 times 10 to the power of negative 4. Of course, I am highlighting this to show that all we are doing with this 4.8 times 10, 48, and that's all there is to it. 2 times 10 to the negative 4. Nice. One should not expect to see a rational square root for a number that has an odd number of decimal places. So there is no rational square root for a number that has an odd number of decimal places. Why? The reason is that when we square a number, the number of decimal places double. The only number that have definite square roots are square numbers. Only square numbers have definite square roots. And if we square a number, the number of decimal places will double. But this, we have here 3 decimal places. It does not represent the double of anything. So we are sure that it will not be rational. So the only number that have definite square roots are square numbers. 1.073 is not a square number, because if it were, its square root would have half of the number of decimal places that it has. So the square root of 1.073, if it has a definite square root, that square root will have half of the number of decimal places that it has. It has 3 decimal places, and I am sure that you have never seen a number with 3 over 2 or 1.5 decimal places. Therefore, for 1.073, we expect that the square root has to be irrational, and it is best determined by using a calculator. Square root, if it exists, will have half of the number of decimal places. We have 3 decimal places. A half of 3 is 1.5. We have never seen 1.5 decimal places. Therefore, this square root of this number is not rational, and we will move to our calculator. Not very nice. And that is the horrible answer that we get. But that is not the test. The test is writing that number that we have there correct to 3 significant figures. This we will write correct to 3 significant figures on the next slide. Now we may go straight ahead and write the number correct to 3 significant figures. Locate the third digit in order of significance by counting from the left, which is where we will find the most significant digit. Start at the most significant digit and count 3. 1, 2, 3. Check the digit that is next in order of significance, the one to the immediate right. The digit is 5, which is greater than or equal to 5. It is equal to 5. And if it is greater than or equal to 5, then we will add 1 to the digit in question, which is this 3. So add 1 and we get 4. The other digits that are located to the left are not affected and return as they are. .04. We are about to divide a decimal by a whole number. We may therefore move to the problem, as we do not have to make any adjustment to the decimal places. Why? As it would have been in the case that the divisor had an accompanying decimal fraction. So the divisor does not have an accompanying decimal fraction, so we do not need to make any adjustment to the decimal places. We may go merrily along and divide. Quickly to the next slide. What do we do? First we say 15 into 0, and that is not possible. Place a 0 over the 0. The answer will not have a whole number part, so we follow the 0 by a point. Why? Because we say 15 into 0, 0, follow that by a point. Because we are going beyond the point. We are sure that we are out of whole numbers, because we know that on the left side of the point we have whole numbers. If we are dividing into this number, we encounter the point and go beyond the point, then we know that we are out of whole numbers. Therefore, anything that follows has to be a decimal fraction. So we include the point right there. Next we say 15 into 2. Also not possible, so we place a 0 over the 2. Like that. 15 can divide into 27. We know the multiples are 15. 15 can divide into 27 only once, because we know the next one is 30. 15 times 2 is 30. It is 27 once. We then multiply 15 by 1. So we say 1 multiplied by 15 that we intend to take away from 27. And when we subtract that, we get 12. Nice. 15 cannot go into 12. We therefore include the 3. Nice. We are always saying that we put an arrow here, say that the 3 should go down here. When the 3 goes down here, how is it that the 3 remains here? Well, that is why we have this computer that can replicate the same thing in a nice way like that. What do we say after that? Well, knowing the multiples of 15, 120 is 15 times 8. Therefore, 15 can go into 123 8 times. Because it is more than 120, therefore, if it can go into 120 8 times, it should at least be able to go into 123 8 times. But only 8 times, because we know that we do not have an extra 15. Okay, look at it this way then. How do we know immediately that 15 can go into 128 times? Well, we are hoping that you would know beforehand that 15 into 60 is 4. But 120 is 2 times 60. So it's 2 times 4, which is 8. There's nothing to it. And of course, we could say 8 times 15, but we know it is 120 already, so we subtract it there. And what do we get? 3. What do we do after that? 15 into 3? 0.3? No. we include a 0. We know that 15 cannot divide into 3, and we do not have any other digit. We therefore include a 0. As before. Finished, because we are sure that 15 into 30 is 2 times exactly. There. And 2 times 15 is 30. And subtract. And the result is 0. Nice. Go to the next slide and write the answer correct to 2 decimal places. We will now write the answer correct to 2 decimal places. 0.0182. Locate the second decimal place 2 digits to the right of the decimal point. That is where it is. Check the digit that is next in order of significance, the one to the right. The digit is 8, which is greater than or equal to 5. We therefore add 1 to the digit in question. The other digits are not affected and return as they are. When rounding numbers, if the digit next in significance to the digit in question, the digit in question is this one. The one next in significance to it is this. If it is 5 or more, we add 1 to this one. So, if it is greater than or equal to 5, then 1 is added to the digit in question. In this particular case, the digit in question is the one in the second decimal place. Why the one in the second decimal place? Because we are writing the answer correct to 2 places of decimal. All of the steps in this problem may be taken mentally. However, let us keep our promise to show how we may solve the ones that do not require a calculator. We have made a promise that as long as it is not so harsh like irrational square roots and so forth, that we will proceed without the use of a calculator. That is the case. Therefore, we will proceed without the use of the calculator. All of the steps in this problem may be taken mentally, but we will show how each one of them is to be taken. For the second number, and by the way, what are we doing? This is what we are doing. 2.8 plus 1.36. That's what we are doing. So for the second number, ensure that the points are vertically aligned. We are adding those numbers and we are ensuring that the points are vertically aligned. And after aligning the digits vertically, aligning the points vertically, what do? Write the digits on both sides, or distribute the digits on both sides, like that. Place holding 0. Any place holding 0? 1 right there. Let's go straight ahead and add the numbers beginning at the least significant digit. 6. 8 plus 3, 11. 1, carry 1. And do not forget that in the answer, the point, the decimal point of the answer should be vertically aligned with the others. So align the points in the answer with the others. And then finish up by saying 1 plus 2 plus 1 is equal to 4. Very nice. That's the addition part of it. Any other? Let us do the subtraction step. And the subtraction step that is in the denominator. The number that we are about to subtract from 4 has 1 place of decimal. 4 does not have any. In order to facilitate the subtraction process in the region of 1 place of decimal, we will assign a place of decimal to 4. In order to facilitate the subtraction process in the region of 1 place of decimal, so we will give that one 1 place of decimal also. We will then place the other number below 4.0 with the decimal points vertically aligned. In addition and subtraction, the vertical alignment of the decimal points is necessary and set up our subtraction problem. On the next slide, we will carry out the subtraction process. We will go straight ahead and complete the subtraction process, but we cannot take 7 from 0. So we go to the next column, use 1 from that position and bring it to the less significant position. There, 3, we are removing 1, taking it here. The digit from the more significant position is 10 times the digit in the less significant position. 10 minus 7 is equal to 3. Of course, we have already discussed on 2 previous occasions why just throwing in the 1 right here and calling it 10 is not illegitimate, but perfectly safe to use. We will ensure also that the point in the answer is vertically aligned with the points in the problem, and those are also vertically aligned. And 3 minus 2 is equal to 1. 1.3. And by now, we are eagerly anticipating the division by 1.3. Exciting long division. The divisor has 1 place of decimal. We will therefore eliminate that place of decimal and increase the dividend by 1 place of decimal also. So the divisor, 1 place of decimal, eliminate that. And also increase the dividend by 1 place of decimal. Let us now eliminate the point from the whole number, because we do not need any more point because it's not a fraction. But the point in the dividend cannot be removed because it is essential to maintain the value of that number. So we have 41.6 and we are dividing that by 13. We will now move merrily, literally merrily, to the next slide where we will have some fun with our long division and decimal fraction. Long division and decimal fractions. First, we say 13 into 4, and that is not possible. But we have not yet exhausted the whole numbers. Why? Because we have not gone past this decimal point. So we say 13 into 4. Not possible. But we have not yet exhausted the whole numbers. Next, say 13 into 41. We know the multiples of 13. 13 times 3 is 39. The answer here is therefore 3. Because we know that 13 3 is 39 so close to 41 but a little less than 41, we are sure that 13 will also be able to go into 41 3 times. Then what do we say? 3 times 13 and subtract that from 41. But we know 3 times 13 already. So subtract 39. Right. 41 minus 39. No one can guess that that is equal to 2. We have exhausted the whole numbers. The next division will result in a fraction. We may now include the decimal point as a part of our answer. Maybe we should have not included the decimal point as yet. But as soon as we include the 6, then we may include it. Well, basically, if we should look at the time, we have 2 types of time or timing on that exercise that we are doing. The time, which is time as we know it with the clock ticking, and the time in terms of relative to each step of the process. It may have been appropriately included after we have included the 6. But I am sure that if we do that before or after, that it does not affect the timing of the problem, because right here and now is an appropriate place to place this point, because we are going beyond the whole numbers now. So we may include the point, and we do not have to wait until we have encountered the fractions. So as long as we have exhausted the whole numbers, we may place the point right there. We already know 13 multiplied by 2 is equal to 26. It's 26. 13 2 is 26. We are finished. The next step is multiply 13 by 2 and take the result from 26. But we know what the result is already. And we subtract that and the result is 0, and we are done. Very nice. This is what we need to be able to do just in case we do not have a calculator at our disposal. But someone is saying everybody has calculators. Good. But it is not every time we will have them at our disposal. Well, you will say that you have yours all the time. Well, I would like to see you bringing your calculator into an examination that does not require its use, or in which its use is forbidden. If those invigilators ever catch you using the calculator in that examination, cheating is not something that you get a slap on the wrist for in CXC. So especially in your multiple choice examination, avoid your calculator. Set it apart like a sore thumb. Treat it, as we would say, like a sea egg. Additionally, some people cannot remember all of the processes taught to them in primary school because of the willful dependency on the calculator. That has caused a part of our skull to be numb, and if we are not careful, we will all become, if a part of our skull is numb, we will all become, you know what. We have a nice problem, and someone would probably look at the original thing and say, well, which nitwit would attempt to solve this problem without using a calculator? Well, If solving it without the use of a calculator makes an individual crazy, then here goes. When we have a product that involves two numbers, one imagine that the one with the larger number of digits will be the multiplicand. But a second look at the numbers reveals that the alternative is better, which is use the one with the larger number of digits as the multiplier. We will see how a wee bit of common sense can make a mathematical process much simpler. Let us begin with the least significant digits. So 5 2s, 10, 0, carry 1. 5 7s, 35 plus 1 is 36, 6, and carry 3. Then what? It's not bad now. 5 times 9 is 45. 45 plus 3 is 48. Nice. That's a breeze. What about the next one on the next slide? We will take the opportunity to multiply by 12, since we know our 12 times table. Also, we skipped the 0. We did not use the 0 to multiply anything. Therefore, the next answer will begin 2 digits in the more significant direction. We will therefore include 2 placeholding zeros before multiplying by 12. That's a lot. We need to multiply by 12. Let's say that we did not do it this way, and we did what? Put the 12.05 here, then multiply by 9.72. What would we have to do? Multiply by 2, then multiply by 7, then multiply by 9. So we would have 3 rows of products. But now we are saying use 5. This is the result of using 5. Then use the 12 because we know our 12 timetable. What can be difficult about that? Also, notice that this 2 in the 12 is what? How far from this? How far from 5? 2 digits in the more significant direction. Therefore, we will begin this answer 2 digits in the more significant direction than the one that we have right here. And that necessitates us including 2 placeholding zeros. So we say 12 2s, 24. So 4 carry 2. Then we say what? 12 times 7 is 84. 84 plus the 2 that was carried, 86. 6. Carry 8. 8 is another number. You may say that from you were born, you have never carried 8. So what if you have never carried 8? That does not make it less possible. So carry 8. Then what do we say? 12 times 9, 108. To 108, we add the 8 that we have carried and we get 116. Because there is nothing left, we just put in that 116. And our number will be nice on the next slide. Right here, I think we'll do it. Let's see. On the next slide, as a matter of fact. Proceed to add the results of the 2 multiplication processes. 0 plus 0. I do not know what that is. 0. And then we have 6 plus 0, and that is equal to 6. What about 8 plus 4? 12. 2, carry 1. Then all of those will be added. 1 plus 4 plus 6 is equal to 11. 1 carry 1. Then what? 6 plus 1 is 7. And then nothing to add there. That is our answer. What do we need to remember? The number of decimal places in the product will be the sum of the number of decimal places in the multiplicand and multiplier together. 1, 2, 3, 4. Together they have 4 decimal places. The answer will have 4 decimal places. So 4 decimal places here, the answer will have 4 decimal places. Very nice. 117.1260. The trailing 0 may be ignored as we move to the next slide, in which we are required to write the answer correct to 2 decimal places. Locate the second decimal place 2 digits to the right of the decimal point. Second decimal place 2 digits to the right of the decimal point. Nice. Second decimal place. Check the digit that is next in order of significance, the one located immediately to the right. The digit is 6, which is greater than or equal to 5. If it is equal to 5 or more, we will add 1 to the digit in question, which is 2 in this particular case. So 2 plus 1 is 3. And what do we know? The other digits are not affected and return as they are. Lovely. When rounding numbers, if the digit next in order of significance to the digit in question is greater than or equal to 5, then 1 is added to the digit in question. In this particular case, the digit in question is the 1 in the second decimal place. Why? Because we are writing correct to 2 decimal places. So the 1 in the second decimal place is our digit in question. And if the 1 less insignificant or to the right of that 1 is 5 or more, we will add 1 to that digit in question. That is why we end up with this 3. We may write the answer correct to 2 significant figures. Locate the second digit in order of significance by counting from the left, which is the most significant digit. 1, most significant to the left. 2, the one next to it. Check the digit in the next position of significance, which is to the right. The digit is 7, which is greater than 5. We therefore add 1 to the digit in question. Well, if it were 5, we would still add 1 to that digit in question. And 1 plus 1 is 2. The other digit, well, in this particular case, is a single one. So the other digit is not affected and return as it is. Rounding is a matter of making an approximation. There is no way that we can imagine that 12 is an intelligent or correct approximation of 117. 12 cannot approximate to 117. A place holding 0 is therefore necessary to maintain the order of the number, and we imagine that 120 is the fair approximation of 117. We will write the answer obtained on the previous slide in standard form. When writing a number in standard form, the number is written in such a way that there is only one non-zero digit in front of or to the left of the decimal point. There we have 117.126, and that is to be written in standard form, which requires that we only have one non-zero digit to the left of the number that will be in our presentation. In order to do that, we need to know how to adjust the number in order that we will do the reverse in maintaining the original value of the number. So count the number of decimal places that will represent the difference between the original number and the number written in standard form. How many decimal places? 0 with no movement. 1, 2. So we have 2 places of decimal right there. The number is reduced by 2 decimal places. The number is therefore divided by 10 to the power of 2. So here we have the number written like so, 1.17126. Notice, come on, we are sure that this number is smaller than this, and it is smaller than this one by 2 places of decimal. 2 places of decimal is related to 100, 10 to the power of 2. Therefore we have adjusted this by 2 places of decimal, 100 or 10 to the power of 2. And this one is definitely the smaller number, therefore we would have divided by 10 to the power of 2. What do we do if we divide by 10 to the power of 2? We need to recover the original value of the number by multiplying by 10 to the power of 2. There it is. We may consider a number that initially had digit or set of digits greater than 0 to the left or in front of the decimal point as a large number. As a rule, we may say that numbers that were initially large should be accompanied by positive powers of 10 in the end. The number of decimal places by which one number differs from the other will tell us the size of the power